Hi everyone, my name is Deyu from Beijing University of Posts and Telecommunications. Today, I'm very glad to introduce our recent work, Structural Deep Clustering Network. This work is done jointly by researchers from BUPT, Tencent, and THU. Okay, let's begin. In this talk, I will first introduce some research background and motivation of our work. Then I will present our model and experimental results in detail. Finally, I will summarize our work. Let's begin from the background. Clustering is a fundamental task in data analysis. It aims to group similar samples into the same category. In the past decades, clustering has been successfully applied to various real-world applications, such as image clustering and text clustering. Let me give a brief review of the development of clustering. There are two stages: clustering on raw data and clustering on representation. The classical clustering algorithms aim to find the best partition on the raw data, such as k-means, hierarchical clustering, and density-based clustering. Spectral clustering is a two-step clustering method. It first learns representations through the cutting of graph, then groups the representations. Recently, as a new trend of clustering, deep clustering, which draws inspiration from the deep learning approaches, achieves state-of-the-art performance and has attracted considerable attention. So, what is deep clustering? It aims to incorporate neural network and clustering objectives together. There is a figure to show the partition process of deep clustering. From the left to right, the raw data are fed into a neural network to learn preliminary representations. Then, a clustering objective is used to group the samples and fine-tune the data representations. Finally, the neural network will learn a clustering-friendly representation. So learning an effective representation for clustering is a crucial requirement. Although deep clustering has made great performances, it still has some problems. Existing methods employ encoder and decoder architecture to learn data representations, ignoring structural information. However, structural information is important in learning representation, such as spectral clustering and graph regularization. This inspires us to add the structural information into existing deep clustering architecture. How to add structural information into deep clustering? There are two challenges. The first is what structural information should be considered in deep clustering. As we all know, there are many structural information, such as first order and higher order. The second is what is the relation between the structural information and the deep clustering? The architecture of deep clustering is complex, so its structural information is not an easy task. Based on these two challenges, we designed a structural deep clustering network, a deep clustering framework which can utilize both the structural information and the content information well. Next, I will present our model, Structural Deep Clustering Network, in detail. Before introduce Structural Deep Clustering Network, we'll first give a toy example to show the differences between Structural Deep Clustering Network and the previous deep clustering methods. In the front of this page, shows the architecture of previous deep clustering methods. They jointly train the unsupervised encoder with clustering loss, leaking structural information. In the bottom is our model. It introduces graph convolutional networks to deep clustering. The loss function is a combination of unsupervised loss, clustering loss, and classification loss. Because graph convolutional network can encode network structures and node attributes flexibly, we stack several graph convolutional layers to effectively capture the different structural information. Now I will show the details about the structural deep clustering network. This is the overview, containing 4 parts: DNN module, GCN module, the delivery operator between them, and the dual self-supervised module. DNN module uses autoencoder to learn preliminary representations and assignments. GCN module stacks several GCN layers to aid structural information and classify the samples. Delivery operator aims to transform the representations learned by autoencoder to the corresponding GCN layers. Dual self-supervised module provides the clustering information. Now I will introduce them in turn. DNN module has 2 roles: autoencoder and assignments. Autoencoder are consisted of encoder part and decoder part, which can be seen as a fully connected neural network with ReLU activation function. We use the output of the hidden layers as the data representation. The assignments are calculated by the similarity of samples and cluster centers. Qij means the probability of sample I belongs to cluster center J. Hi is the representation of sample I. Μj is the representation of cluster center J. The distribution Q represents the set of the soft assignments, which will be used in the clustering loss function. GCN module. GCN module uses graph convolutional operator to learn the structural information. To review the underlying structures of the samples, we first construct a KNN graph based on the feature similarity. The graph convolutional operator is based on it. It's worth noting that the features fit into GCN is not the raw features, but the combination of the GCN specific representation and the autoencoder specific representation. To achieve this, we design a delivery operator. It uses a hyperparameter epsilon to control the proportion of these 2 kinds of representations. After propagation, we will calculate the soft classification results. We call it distribution Z. Dual self-supervised module is the clustering loss function, which can be calculated in 4 steps. First, we calculate the distribution P based on Q. This is the blue line. It can be seen as the distribution P can be seen as the distribution Q after square, then normalized. This will make the data representations close to the cluster centers, thus aiding the clustering cohesion. Second, we use a KL divergence to measure the distance between distribution Q and the distribution P. Make the distribution Q close to distribution P. This is the dashed red line. Third, this is also a KL divergence, and make distribution Z close to distribution P. This is also a dashed red line. Finally, the The clustering loss is a combination of reconstruction loss and the 2KL divergence loss. The remark of our work is that we give a serial analysis about the delivery operator and found that it can benefit both DNN module and GCN module. For DNN module, it is the structural information. Especially, we found that the structural information equals to second-order graph regularization. Second-order graph regularization means that two nodes may have similar representations if their neighbors are similar. For GCN module, the autoencoder-specific representations will add additional information to the GCN module, which can alleviate the oversmoothing problem. Through this analysis, we can learn more about the role of our modules. To evaluate the effectiveness of our model, we conduct extensive experiments. We choose 8 baselines. The left 4 methods are feature-based clustering, and the right 3 methods are GCN-based clustering. SDCNQ is the variant of SDCN. We also use 4 metrics to evaluate the clustering performances: accuracy, normalized mature information, average rand index, and macro F1 score. 6 datasets are used. The top 3 datasets are image dataset, record dataset, and text dataset, which uses KNN graph in GCN. The bottom 3 datasets are the attributed network. We use the attributes as the features and the network as the input of GCN. This table shows clustering results. The performance of SDCN and its variant are shown in red box. Obviously, our model performs quite well compared with feature-based clustering methods and GCN-based clustering methods. We also conducted the experiments about variance and propagation layers. In the left, we compare our model with 2 variants to verify the ability of GCN in learning structural information and the effectiveness of the delivery operator. SDCN result means the SDCN without delivery operator. In SDCN MLP, we replace GCN with multi-layer perceptual. From the histogram, we can find that the importance of GCN and the delivery operator. In the right, we vary the number of GCN layers from 1 to 4 to investigate whether SDCN benefits from multi-layer GCN. Obviously, the 4-layer SDCN performs best. The reasons are twofold. One is that 4-layer GCN can fully use the representations learned by autoencoder. Another is that the delivery operator can alleviate the oversmoothing problems. In this experiment, we will explore how SDCN is affected by different epsilon on different datasets. Note that epsilon, when epsilon equals to 0, it means that the representation in GCN module do not contain the representations from autoencoder. And epsilon equals to 1 represents that GCN only uses the representations learned by autoencoder. From the figures, we can find that the clustering accuracy in all data size performs the worst when epsilon equals to 0. Clearly, in this situation, GCN module is equivalent to the standard multilayer GCN, which will produce very serious oversmoothing problem, leading to the decline of the clustering quality. Even at a small amount of representations learned by autoencoder into GCN can help elevate the oversmoothing problem. Since the number of the nearest neighbors k is an important parameter in the construction of the KNN graph, we design a k sensitivity experiment on the data size with KNN graph. We compare SDCN with the clustering methods focusing on the graph data, GAE, VGAE, and DAEGC. We found that with different number of k, our proposed SDCN is much better than GAE, VGAE, and DAEGC, which proves that our method can learn useful structural information, even in the graphs containing noise. So SDCN is a non-sensitive method. Now let's summarize our work. First, we propose structural deep clustering network. To the best of our knowledge, it is the first to use structural information in deep clustering. Second, we give a theoretical analysis of our proposed SDCN and review the effectiveness of the delivery operator. Finally, we achieve the state-of-the-art clustering performances and make detailed experiments. Thank you for listening to our presentation. More materials about our work can be found in this URL, and the code can be found in this. Thank you for listening.